Hello. In this video, we're going to talk about fission and fusion. In this video, by the end of it, you should be able to describe fission and fusion and explain how a nuclear power plant works. So let's start with the idea of nuclear fission. Nuclear fission is the splitting apart of larger nuclei into smaller nuclei and neutrons. It is going to be initiated by the introduction of a neutron. So the neutron itself is going to come in and it's going to cause this fission process. Okay? And nuclear power plants utilize fission reactions in order to produce large amounts of energy. In comparison, so let's do a little comparison of energies. If we look at natural gas, it releases 54 kilojoules per gram. If we compare this to uranium-235, it releases 1.4 times 10 to the 9 kilojoules per gram. So a significantly larger amount of energy is going to be released from uranium-235 versus natural gas. Now, some notes about this fission process. We have to have a neutron that induces it, and we have to have a fissile material. So a common fissile material is uranium-235. Uranium-238 is the most common uranium, but that's not a fissile form of uranium. It has to take in a neutron, break into two fragments, and produce additional neutrons in order to be considered a fissile material. With uranium-238, it will decay and produce alpha particles, but it is not going to produce neutrons that are capable of fission reactions. So let's look a little bit more at this process. Fission, we cause fission when we bombard a fissile material by an accelerated neutron. So fission occurs when a fissile material is bombarded by an accelerated neutron. Okay? It's going to cause the nuclei to break down into two smaller nuclei. The nucleus breaks down into two smaller nuclei. Okay? And once that occurs, it's also going to produce 2 or 3 neutrons, which are also accelerated and can go do more fission reactions. Okay? This continuous generation of neutrons and subsequent fission reactions is called a chain reaction. So a chain reaction is a self-sustaining nuclear fission reaction. And we can see a picture of it over here on the right. As long as we have a massive enough piece of uranium-235, which is actually going to be dispersed through a larger portion of 238 uranium, so we don't have too great of a reaction that occurs, it will keep going until you use up all of the 235. Now, we have something that's called the critical mass. The critical mass is the mass that must be available in order for a chain reaction to occur. If we do not have that amount, then we do not have we don't have the ability to do a chain reaction. Less than that amount, less than that critical mass, are what we call a subcritical mass. We will have the neutrons leaving the material and it won't continue doing fission reactions. If we do have the critical mass, it'll just keep going over and over again. So this is how nuclear power plants work. We also have something called the supercritical mass. And this is a mass large enough for a bomb. Nuclear power plants are going to work by having chain reactions so that they can have the reaction occur, but they have to have a reaction that is going to be stable and it's going to be controllable. If we have a too large amount of uranium-235, then you cannot control that reaction and then you have a bomb. Nuclear power plants harness the energy generated during the fission of uranium-235. During uranium-235 fission, it releases a lot of energy, and that energy is going to be generating heat, and that heat actually heats up water and generates steam. That steam is what actually powers the generator in a nuclear power plant. So if we look at this picture on the right, we have our uranium fuel right here. So it's going to be 238 uranium with enrichment of 235 throughout. Again, not too much. We don't want to cause an explosion. And there's also these things called control rods at the top that are there to control the reaction if it seems to be getting too energetic. And then there are steam generators that are connected or touching the tubes right here. So we've got these tubes or pipes that have a lot of energy and they are heating up the water and generating steam. And then that steam is going through steam lines to a turbine, which is then powering a generator, which is then transformed and made into energy. And through all this, there's only water vapor produced. Of course, there's also nuclear waste that's produced and the possibility of radiation leaks and the possibility of a nuclear meltdown. So there are some issues, but it is generally considered a cleaner form of energy. And let's real quick just look at the idea of nuclear fusion. So nuclear fusion is when we join two light nuclei together. This is what the sun does, and all stars. Do. Okay. It also generates a large amount of energy, 2.2 times 10 to the 9 kilojoules per gram, so a significant amount, even more than the fission does. But this is not something that has really been able to be harnessed at this point because fusion reactions require a large amount of heat and pressure. So even though nuclear fusion, that power plant would be cheap, clean, and the nuclear waste would not exist in there, there are extreme experimental conditions that have to be achieved in order to get fusion to occur. So the experimental conditions. You have to have 1 times 10 to the 8th degrees Celsius temperature and 1 times 10 to the 5th atmospheres of pressure. So very, very large amounts of heat and pressure are required to cause a fusion reaction to occur. And even though you get a lot of energy out, we don't really have at this point the ability to cause this reaction to occur safely and conveniently. Okay, that is everything for fusion and fission.